how Newton might interpret gravity was adequate to permit us to fly from the Earth to the Moon. At any point, get yourself lost in the ticking hands of time, contemplating whether our understanding of it is simply the tip of the transient icy mass. On its head, his disclosure isn't simply a hypothesis. It's a key that could open the ways to the secrets of the universe, uncovering a cosmos more complicated and inspiring than we ever dared to imagine. How does Brian Cox's new hypothesis challenge our conventional comprehension of time, and what are the potential implications for our view of reality? Join us on a fascinating exploration through the archives of time itself, as we delve into Brian Cox's recently revealed groundbreaking hypothesis on the nature of time in the vast universe around us. Secrets are waiting to be uncovered, and some of these secrets involve perplexing aspects of time and gravity, which are fundamental components of our reality. Imagine a world where time acts strangely. It can either slow down or speed up. Likewise, the force that keeps us on the ground might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes an unexpected turn. Albert Einstein, a notable figure, provided us with a new way of looking at the universe through his theories of relativity. His work laid the foundation for understanding how time behaves in different circumstances, particularly when traveling at extremely high velocities. It all started in the early 20th century when Einstein proposed two remarkable theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, revolutionized our understanding of reality. In simple terms, it tells us that the laws of physics remain the same for all observers who are not accelerating, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous idea that time can dilate or slow down under certain conditions. One intriguing analogy used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, almost at the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors, perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers. Thus, the light beam must appear to travel a diagonal path. Here's the fascinating part. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the external observer, it seems as if it takes more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer, moving relative to the stationary observer. Understanding how things change when they move fast, known as relativistic effects, isn't just a theoretical concept. Scientists use large machines called particle accelerators, like the Large Hadron Collider, to make particles move incredibly fast, almost at the speed of light. When objects move this quickly, we have to think about time in a special way to make accurate predictions and calculations. Einstein's special theory of relativity challenges our everyday assumptions. It states that the principles of physics are the same for everyone, even if they are moving. This contradicts our usual experience, where we assume that if something is already moving and we add more speed, it gets faster. However, Einstein's theory says there's a maximum speed. Nothing can go faster than the speed of light. In this framework, events that appear to occur simultaneously to us might not seem that way to someone moving close to the speed of light. Another consequence of this extraordinary perspective is length contraction. This means that if something is moving, it appears shorter in the direction it's moving when viewed from a stationary point. Then there's Einstein's famous equation, which shows that energy and mass can be converted into each other. This has profound implications for understanding how tiny particles behave at high speeds and for phenomena like nuclear reactions. Special relativity isn't just a fancy theory. It's something we use in everyday technologies like GPS. When GPS satellites transmit signals to your device, they are moving, and because of this motion, time behaves slightly differently for them. If we didn't account for this time dilation effect in our GPS calculations, your navigation would be off. So, special relativity teaches us that time isn't the same for everything and everywhere. It depends on how things are moving. This idea challenges our typical understanding of space and time. It's like saying our normal perception of the universe is a bit flawed. Einstein's general theory of relativity, proposed in 1915, goes deeper into the relationship between gravity and the structure of the universe. It disrupts the old idea that gravity is just a force pulling things from a distance. Instead, it tells us that gravity occurs because space and time are curved or warped. It's like saying, hey, gravity isn't a mysterious force. It's just how things naturally move in the universe. To understand general relativity, imagine space-time as a large, stretchy sheet. When a heavy object like Earth is placed on it, it creates a dent in the sheet. If you place something smaller like a ball near Earth, it will roll toward the dent. This is similar to how objects behave due to gravity, not as a mysterious force, but as a response to the bending of space-time. General relativity provides a powerful explanation for how things move in our solar system, like the planets orbiting the Sun. It accurately predicts the paths these planets take, including Earth's elliptical orbit. This is different from the old idea of gravity, simply aligning things, which struggled to explain planetary motion. A groundbreaking moment that confirmed general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed near the Sun. According to the theory, the Sun's massive gravitational field would bend the starlight slightly during the eclipse. Observations matched Einstein's predictions, validating the theory. Just as motion can alter our experience of time according to special relativity, gravity also affects time. Where gravity is extremely strong, time moves more slowly compared to regions with weaker gravity. If you stood near a massive object like a black hole, your clock would tick more slowly than one far away from this immense mass. General relativity also introduces black holes, regions where gravity is so intense that nothing, not even light, can escape. The boundary around a black hole is called the event horizon, a point of no return. Once something crosses this threshold, it gets pulled into the black hole with no chance of escape. Einstein's general theory of relativity has profound implications for how the universe is structured. Initially, Einstein added a cosmological constant to his equations, believing the universe was static. However, when we discovered it was expanding, he called this a major mistake. The idea of an expanding universe, rooted in general relativity, is a cornerstone of the Big Bang theory, which explains how the universe began. Einstein's theories of relativity, both special and general, have reshaped our understanding of the universe, challenging long-held assumptions and opening new doors to scientific discovery. They provide a framework for understanding phenomena on cosmic scales, such as the behavior of galaxies, black holes, and the expansion of the universe, as well as on the tiniest scales, like the behavior of subatomic particles. One of the most fascinating predictions of general relativity is the existence of wormholes, hypothetical tunnels through space-time that could theoretically connect distant parts of the universe. While purely speculative at this point, wormholes have captured the imagination of scientists and the public alike, offering intriguing possibilities for time travel and interstellar exploration. The interplay between time and gravity has profound implications for our perception of reality. For instance, time dilation near massive objects like black holes raises questions about the nature of time itself. What would it mean for a human to experience time differently near such objects? Could this phenomenon provide clues about the ultimate fate of the universe or the possibility of alternate dimensions? Einstein's work also laid the groundwork for the field of cosmology, which seeks to understand the origins, structure, and evolution of the universe. Concepts like the Big Bang, dark matter, and dark energy all trace their roots back to the principles of relativity. Dark energy, in particular, poses one of the greatest mysteries in modern science. It is thought to be responsible for the accelerating expansion of the universe, a phenomenon that challenges our current understanding of physics. Building on Einstein's legacy, Contemporary physicists like Brian Cox are exploring new theories that push the boundaries of our knowledge. Cox's ideas challenge traditional notions of time and space, proposing that time may not be a linear progression, but a more complex and interconnected phenomenon. Such theories invite us to rethink fundamental aspects of existence and consider how they might impact our understanding of the universe. For instance, quantum mechanics, another groundbreaking field of physics, offers a contrasting perspective on the behavior of particles at the smallest scales. Reconciling quantum mechanics with general relativity remains one of the biggest challenges in physics today. The search for a unified theory, often referred to as the theory of everything, aims to bridge the gap between these two pillars of modern science, providing a comprehensive framework for understanding the universe. Experiments in cutting-edge facilities, such as the Large Hadron Collider, are helping scientists probe the fundamental building blocks of matter and energy. By recreating conditions similar to those present at the beginning of the universe, researchers hope to uncover clues about the nature of space, time, and gravity. These endeavors are not only deepening our scientific understanding, but also inspiring new technologies and innovations. As we continue to unravel the mysteries of time, gravity, and the universe, one thing becomes clear. The more we learn, the more questions arise. Einstein's theories remind us that the universe is far more complex and wondrous than we can fully comprehend. Yet, with each discovery, we take another step closer to understanding the fundamental nature of reality. Whether seeing how planets move, the bowing of starlight, or the discovery of gravitational waves, the hypothesis has reliably been upheld by proof. While saying gravity is obviously false may be astounding, particularly since we all experience gravity consistently. In the universe of physics, it's not uncommon to discuss and explore various ideas. Scientists like Brian frequently question established theories, and with gravity, certain individuals challenge the usual way we think about this fundamental force. One idea testing conventional gravity is called modified Newtonian dynamics, MOND. MOND proposes that gravity acts differently at slow velocities, particularly in galaxies, without requiring dark matter. Instead of adding invisible matter, MOND suggests that gravity gets stronger at low rates. The gravity debate also involves puzzling dark matter and dark energy, introduced to explain certain phenomena in space. Critics argue that these are not needed and that alternative ideas can explain what we observe. Some scientists who disagree with Einstein's theory of gravity explore additional possibilities, such as theories involving unknown particles or forces that could modify or add to our understanding of gravity. It's vital to understand that in science, new ideas are not ignored. Rather, they are carefully tested to see if they make sense. For instance, Einstein's idea about time in four-dimensional space, where traveling back in time might be limited by the speed of light, has been creatively considered alongside concepts like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that traveling back in time seems unlikely from a physics perspective. Ongoing experiments and observations test whether these new theories can explain phenomena like the force of gravity in a similar way to what we already know. While various ideas have been discussed, none have convincingly replaced the well-established principles of gravity. Questioning and opposing ideas are essential parts of how science learns new things, leading to further research and a better understanding of the universe. In the realm of gravity theories, general relativity remains the most significant and successful one. Despite challenges and alternative ideas, it consistently performs well in tests and explains various phenomena, such as how planets move and how light bends around massive objects. General relativity remains strong because it is simple and covers a wide range of phenomena. As we discussed earlier, Einstein's special theory of relativity suggests that time can act differently depending on how you're moving. Now, let's explore how this idea affects real-life situations, especially in space travel. Space travel is exciting but challenging because space is vast. And according to Einstein's theory, the speed of light is the fastest anything can go. This makes traveling between stars a huge challenge, even with cutting-edge technology, because of the lengthy time it takes to reach the nearest stars. Consider the famous twin paradox to understand what happens with time when you travel in space. Picture this: one twin stays on Earth while the other twin goes on a trip to a faraway star. When the space-traveling twin returns, they find that less time has passed for them than for their twin on Earth. This means they effectively traveled into the future. Time is crucial for space travelers because the longer the journey, the more time slows down. If astronauts travel to nearby stars where time slows significantly, they could age more slowly than people on Earth. While it may sound like science fiction, it's a real effect predicted by the theory of relativity. Imagine if humans sent a crew to a star system not too far away. Because it's such a vast distance, the journey could take many years, even if they travel fast. For the astronauts on the spacecraft, time would feel shorter due to this time dilation. However, on Earth, much more time would have passed. Time dilation affects not only living beings but also technology. Computers and communication devices on spacecraft must account for time dilation to ensure accuracy and proper functioning. Space travel challenges at high speeds include physical aspects like extended isolation, exposure to intense radiation, and the psychological effects of being away from Earth for long periods. In our daily lives, we can observe the effects of time dilation in the Global Positioning System, GPS. GPS relies on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it's crucial to account for these effects for accurate GPS measurements. Failing to do so would significantly affect the accuracy of navigation systems. Now, let's explore why time moves in one direction. Time governs our lives in the universe, moving from the past to the present and into the future. This one-way journey of time is fundamental to our existence. But why does time have this one-way nature? To understand, we look at entropy, a concept measuring disorder or randomness in a system. Entropy, linked to the arrow of time, tends to increase over time, making time flow in one direction. The second law of thermodynamics expresses this relationship, stating that in any isolated system, total entropy will either increase or, at best, remain constant. In simple terms, entropy naturally tends to grow and doesn't decrease on its own. Observing how things become more disordered around us helps us see the one-way flow of time. Imagine a deck of cards perfectly organized. If we shuffle them, they become messy and random. This change from order to disorder shows how time moves in one direction. As seen in everyday phenomena like ice melting or a stirred cup of coffee becoming mixed. This flow of time works differently at various levels. At the level of small particles, the laws of physics allow things to move backward and forward in time, a concept known as time reversal symmetry. The discrepancy between this and the irreversible changes we see in the everyday world comes from something called initial conditions. The large, complex world we live in is the result of many particles interacting, creating a one-way arrow of time. The idea of time moving in one direction isn't just about everyday things. It's also true on a cosmic scale. The entire universe has been evolving in one direction since the Big Bang. The universe started in a low-entropy state, and over billions of years, it has become more disordered, forming galaxies and stars. Scientists are still figuring out why the universe began in such an ordered state. Even in the tiny world of quantum mechanics, which deals with subatomic particles, there is a time arrow. The way particles change over time seems symmetrical, but when we observe them, things become irreversible. Brian believes that this isn't just a physics issue. Our brains also experience time in one direction. We remember the past, live in the present, and think about the future in sequence. This psychological arrow of time is connected to how we perceive the external world's arrow of time. This concept of time has profound philosophical implications, challenging how we understand reality. Time is a fundamental part of how we experience life and comprehend the world around us. Without this one-way flow of time, everything would be entirely different, with no consequences for our actions, and cause and effect relationships wouldn't make sense. The concept of time travel into the future, as suggested by Einstein's theory, has fascinated both scientists and the public. Although we have not yet achieved space travel at speeds close to that of light, Experiments involving particles, such as those conducted in particle accelerators, provide evidence supporting time dilation. For example, high-speed particles decay more slowly compared to their stationary counterparts, demonstrating how time passes differently under extreme conditions. For practical space travel, however, the challenges are immense. Achieving near-light speeds requires extraordinary amounts of energy, far beyond what our current technology can provide. Additionally, the effects of time dilation could create profound social and psychological consequences for astronauts. Imagine returning from a space mission to find that decades, or even centuries, have passed on Earth, while only a few years have gone by for the travelers. This would create a disconnect between the astronauts and the society they left behind. Despite these challenges, future advancements in propulsion technology and energy sources might bring us closer to achieving such feats. Concepts like antimatter propulsion, warp drives, or using massive gravitational fields to bend space-time could someday become feasible, though they remain speculative at this stage. If humanity does develop the ability to traverse vast cosmic distances, the effects of time dilation will likely play a central role in shaping our understanding of long-term space exploration and our place in the universe. While the idea of traveling into the future is grounded in the laws of physics, traveling into the past remains far more controversial. Wormholes, hypothetical shortcuts through space-time, are often proposed as a theoretical means of achieving this. However, creating or stabilizing a wormhole would require exotic matter with negative energy, a type of matter that has yet to be discovered or proven to exist. Even if such a phenomenon were possible, it could lead to paradoxes, such as the grandfather paradox, where a time traveler could theoretically alter the past in ways that prevent their own existence. Stephen Hawking's chronology protection conjecture suggests that the laws of physics may inherently prevent time travel into the past to avoid such paradoxes. This idea aligns with the broader understanding that while the future remains open to exploration, the past may be inaccessible, locked away by the one-way arrow of time. In the broader context of human curiosity, our fascination with time travel reflects our desire to transcend the limitations of our existence. It raises profound questions about the nature of time, reality, and our role in the cosmos. Whether through scientific breakthroughs or philosophical insights, the exploration of time continues to inspire humanity to push the boundaries of knowledge. The study of time dilation, entropy, and the arrow of time has practical applications beyond theoretical physics. From enhancing GPS accuracy to understanding the early universe, these concepts influence technology, cosmology, and our daily lives. As we uncover more about the nature of time, we may find new ways to navigate its flow, perhaps even unlocking mysteries that redefine our understanding of reality.